friends, and in this video we are going to discuss about the first principle, the differentiation with the help of first principle. This is also called ab initio method or the first principle method. So it goes like this: differentiation using first principle. First principle or ab initio method. This method is, suppose if we have y equal to function, y is a function of x, and that is graphically plotted like this. Take a point P here with the coordinate as x comma fx, and little far away from this there is another point called Q with the coordinate x plus h comma f x plus h. Now join these two lines, you will find that they form a chord. So if I try to find the rate of differentiation, f dash x, find the slope, so this theta, so we have tan theta, that is called the slope of the chord PQ, that is, it is called as y2 minus y1 upon x2 minus x1, or in other word, if you just pay attention that this point is x, so this distance is x here, and this distance from here to here it is x plus h. So from to here this distance is just h, and this point corresponding to this is your fx, and corresponding to the point Q you have your part of your function, that is fx plus h. So this distance will be fx plus h minus fx. So the slope will become fx plus h minus fx over h. And if you just provide a limiting value like the limit h tends to 0, so this chord when h tends to 0 will become, when the p and q coincides, then this chord will become the slope of this curve, and that will become tangent somewhere like this. And that is the idea of this principle, because indirectly we are trying to find out the slope or change of y component with respect to change in x component, and this is called as f dash x. So the definition of the first principle or ab initio method becomes f dash x is limit h tends to 0 fx plus h minus fx over h. Now this is the graphical representations on significance of this equation. Now I want to take some examples to solve and apply to find out this derivative using first principle. For that I need to clear up the screen. Suppose we have a function called fx equals sin x, then we need to find fx plus h. So fx plus h is sin x plus h. Now f dash x is limit h tends to 0 sin x plus h minus sin x over h. Now limit h tends to 0, this one. Now this is the form of sin c minus sin d. Sin c minus sin d is 2 cos c plus d by 2. So x plus h plus x over 2 into sin x plus h minus x over 2 whole divided by h. So this one now you see becomes limit h tends to 0. This 2 I am just trying to put it down, so this will become h by 2, and this part is cos 2x plus h by 2 into sin h by 2. Now I'll separate these two. and provide them separate limit values for them. So limit h tends to 0, cos 2x plus h over 2, and limit h tends to 0, sin h by 2 over h by 2. This one, you know, by formula it is 1, because the formula says that limit theta tends to 0, sin theta over theta is 1. So here limit h tends to 0 and h by 2, because h by 2 also should be 0, since h tends to 0. If h tends to 0, therefore h by 2 also tends to 0. So this value becomes 1. And if I put the value of h0 here, because this is going to be a defined number, so it is cos 2x plus 0 upon 2, and this will become cos 2x by 2, and this is cos x. So what we have found, that if fx equal to sin x, then f dash x equal to cos x. This is the basic idea of the first principle or the ab initio method. Now I'll take one more example to solve this question. Okay, so this time I take another complicated function, and this function is fx is e to the power under root sin x. So fx plus h is e to the power under root sin x plus h. Now we write the definition here. F dash x is limit h tends to 0, fx plus h minus fx over h. So this becomes limit h tends to 0, e to the power under root sin x plus h minus e to the power under root sin x upon h. So what I do, that I take limit h tends to 0, I take e to the power sin x under root common. So e to the power under root sin x common. Then I have e to the power under root sin x plus h. Now in the case of indices, when you take something common, so it's coming over this e to the power roots like this, e to the power root sin x minus 1 and whole divided by h. So this becomes limit h tends to 0, e to the power under root sin x. This one can be written as e to the power under root x plus h minus root x minus 1 over h. Now we have to apply a formula that is limit x tends to 0, e to the power x minus 1 upon x equal to 1. And perhaps this is the reason why we have taken e to the power root x come, so that I can get this form. Now since h tends to 0, so e to the power root x is the independent function, because there is no h involving there, so that is just like a constant. So we can write here e to the power root sin x here, and then this becomes limit h tends to 0. So now this part under root x plus h minus root x, this part, this one, if I take it as suppose k, so this becomes e to the power k minus 1 upon h, and then this whole thing. Now what is your k? So I can write here k is under root x plus h minus under root x. So just this is assumption, you can say this is my assumption. Now I want to see this is e to the power x over x, so this e to the power k is h, so this also should be k. So I can write k here, and then I can write here k upon h. So k and k, these two are cancelling each other, and we actually have e to the power k minus 1 over k. Now here if you see that k is under root x plus h minus root x, if h tends to 0, since h tends to 0, Therefore this part k becomes under root x minus under root x, therefore k also tends to 0. So limit h tends to 0 is equivalent to limit k tends to 0 under this light of this assumption. So we will write here as e to the power right under root sin x into, I can write this one as limit k tends to 0 e to the power k minus 1 over k, and then for this part I will let the limit be h tends to 0 only. So that is limit h tends to 0. This is this k over h. So again I rewrite the value of k, that is x plus h minus under root x over h. So now this by formula, this part becoming 1, so this becomes only e to the power root sin x into limit h tends to 0. So now how to find the value of this limit h tends to 0, root x plus h minus root x over h. So first I need to rationalize this. So rationalize this in the numerator, you see there is the under root a minus under root b form. So I'll multiply under root a plus under root b up and down, so to utilize the cases. So it becomes limit under root x plus h minus root x under root x plus h plus under root x over h, and then down also we have to write the same thing, under root x plus h plus under root x. Now if you see the numerator, this is the form of a minus b into a plus b. Perhaps that is the reason why we have multiplied, because already we had something in the a minus b form and we multiplied a plus b so that to get a square minus b square, and individually when these two terms will be squared, their square root will vanish. So you will have x plus h minus x and x plus h plus under root x over h. Sorry, we should not have this in the numerator because that has become a square minus b square. So down we need to have this under root x plus h plus under root x. So this is e to the power root x and limit h tends to 0. Now x and x cancel, h cancel with this one. So you have just 1 over this. So I can write here this only, I don't need this part, 1 over this. So now I can put the value of limit directly, that is h tends to 0, so h will become 0. So 1 by root x plus root x, that is 1 by 2 root x, and this is e to the power root x. This is your f dash x using ab initio method or the first principle method. I think now in the next video we will discuss about how to find the differentiation of a function at a given point using again ab initio or the first principle method. Thank you very much. Subscribe to our channel and keep practicing with us.